Math 1325, we are up to section 5.1, and we're going to be working on a chapter where we see what derivatives tell us. The derivative of function gives us a lot of insight into what's happening to the actual function itself. More detail than you can do just with algebra. So the big concept in section 5.1 is, when is a graph increasing or decreasing? This concept is first discussed in a college algebra type class, although they do it just by looking at graphs only. We're going to be doing it by looking at derivatives. Although I think the first couple problems go back to the way they do it in college algebra first, so that way you'll know what we're doing later. So find the open intervals where the function below is increasing or decreasing. This is exactly what happens in a college algebra class. They travel left or right on a graph. When's it increasing? When's it decreasing? So make sure you are traveling left or right. And it's starting down here. So from negative infinity, because this would just keep going down and to the left forever, even though it's mostly going down. So starting at negative infinity, you would be moving up on this graph. And you would be constantly increasing until you reach this high point right there, which is at an x value of 3. So the graph is increasing from negative infinity all the way till 3. Now you always put parentheses on infinities, but here we always put parentheses on the actual numbers too, because you can't be increasing or decreasing at a single spot. So at exactly 3, nothing's really happening. So all the way till 3, it's increasing. Then suddenly at 3, it's decreasing after that. From 3 until this low point right there of 5. From 3 to 5, the graph's decreasing. So we're going to answer that apparently in the next part. And then from 5 forever on to infinity, it increases a second time. So then it says... use integers or fractions, use a comma. Okay, sometimes they put a union symbol between them, but here they want a comma. And then we're going to go from 5 to infinity. It's going to be increasing a second time. So you can have more than one time that it's doing an increasing or a decreasing. And then it's decreasing just between 3 and 5. So 3 comma 5, that's college algebra interval notation. It looks like a coordinate 3 comma 5, but that's interval notation. Interval notation where you're between 3 and 5. So this is the algebra way of doing it when you look at a graph. And these are simple enough graphs that that's possible. Later we'll get funkier functions that you probably don't even know what the graph looks like, and then really calculus will be the only way to work on it. Now, one thing that's different on this problem number 2, though, is it says, suppose the graph below is the graph of f prime of x, the derivative of x. Find open intervals where f of x is increasing or decreasing. So this can get real tricky the first time you see this, because even though you're decreasing along this graph first, and then you reach this low point, then you increase after that, that's the derivative that's decreasing and increasing, not the regular function. They want to know when the regular function is increasing and decreasing. Well, the main rule that you're about to learn for problems 3 through 10 is that an original function is increasing, f of x is increasing, not f prime of x, but f of x is increasing anytime f prime of x is positive. When a derivative's positive, then the slopes of the tangent line touching that spot will be positive, and that's when it's going up. And it's decreasing anytime the derivative is negative. And that's really easy to remember because positive is up and negative is down usually in most cases. So you're decreasing when the derivative is negative, you're increasing when the derivative is positive. On this graph, this is the derivative graph, so the derivative is positive anytime there's a portion of this graph above the x-axis. So this little portion here that I'm circling from negative infinity until you get to 3. That's entirely above the x-axis, so that's a increasing portion of the regular graph. The regular graph is increasing from negative. You always start at negative infinity because you're coming in left to right. Negative infinity, it's just a coincidence that we got 3 again. It's increasing from, even though the derivative function is going down, it just means it's increasing less and less, but it's still increasing all the way till that point. Then from 3 all the way around to 7, that's all below the x-axis. That's a part where the regular graph is decreasing. And then from 7 to infinity, I have another section that's increasing, because that's another section where the derivative graph is above the x-axis. So if they give you a derivative graph or you draw your own derivative graph, it's not about when that graph is going up and down. It's about when is it above the x-axis, when is it below the x-axis. So between 3 and 7, that's when the original function will be decreasing. And we'll confirm this as we go through this chapter too. Okay, so those two were just looking at graphs. Now we're going to do everything algebraically and with calculus only, no graphs now, although we can look at graphs also later. But okay, so here's an original function. F of x is 2/3 x to the third minus 5x squared minus 72x minus 18. We have a long polynomial here. Part A, find the critical numbers. B, find open intervals where the function's increasing. And C, open intervals where it's decreasing. So the big concept here is a critical number. A critical number in calculus is any zeros or undefined x values of the derivative function. So you'll start with a regular function, f of x. You're going to find its derivative with all the techniques you learned in chapter 4. And then the goal will be set the derivative equal to 0 and or look for spots where that possibly might be undefined. So undefined can happen in a lot more less common areas. It's undefined. It's more commonly that critical numbers come from the zeros of the derivative, but we also have to worry about undefined spots. Now, one little technicality to that is we want undefined x values in the original function, in the derivative function, as long as they're not also undefined in the regular function. Because any x values that are undefined in the original function, that you can't even do the derivative at that spot. You might remember there was some problems in chapter 4 where they gave us a graph. There was one that looked like the Houston Texans logo, where they had a graph that looked like this. And they asked, where are all the x's where there's no derivative? And it turned out in this picture, the only one was that corner point. But we went through a list of things we were looking for, like vertical tangent points, places where there's like a disconnect of the graph, it's discontinuous. Another one was any spots where the original graph is undefined. If a graph's undefined at any spot, then you can't do a derivative there. And if you can't do a derivative, it'll be undefined, but it may be undefined on its own, or it may be undefined because the original function's undefined. So that's the one little technicality, is if the derivative function is undefined anywhere, we have to go back and check real quick, is it also undefined in the original function? If so, then it's not a critical number. Okay, so number 3. Now, one nice thing when you deal with polynomials is polynomials, they're continuous smooth curves. They have no issues in them. So you can find derivatives everywhere in a polynomial. And they don't have any undefined spots. There's no issues with like corner points or vertical tangent lines. So polynomials are nice and clean. Nothing weird about them. Unless just their numbers are high or messy. So 2/3 x cubed. You might think that fraction will make it messy, but actually it won't. Minus 5x squared minus 72x minus 18. A college algebra student might be given a graph like this to find all the zeros, or to graph it with like end behavior and finding intercepts and the zeros. That's the kind of thing we do in college algebra. We don't need to do any of that here. So we're going to find its derivative first. This is a simple term-by-term power rule. So 3 times 2/3. See, that's nice. 3 times 2/3, literally. And then you decrease the exponent by 1. That's nice because the 3's cancel out. So the derivative part is just 2x squared for that term. And then 2 times -5 is -10x to the first. The derivative of -72x is -72, and the derivative of 18 is nothing. So my derivative is a polynomial. Polynomials are never undefined. So there's a highest exponent of 2. So there would be 2 zeros potentially of this polynomial function, this derivative polynomial function. So the original function was third power, and the derivative function second power. That always happens with polynomials. It's always one less. And there could be 2 zeros to this polynomial function. And if there is, then I'll have 2 critical numbers. So then we need to factor this and find the 2 zeros like we were in college algebra again. And one thing that can help is if you can divide everything by 2, that'll at least make the numbers smaller. That doesn't always work, but it did here. So x squared minus 5x minus 36. We need two values that multiply to -36 and subtract to -5 in essence. And I teach algebra students, if there's a negative in the back of a trinomial, you automatically get one positive and one negative in your factoring. Multiply to 36. When there's a negative in the back, you're technically trying to subtract to the middle instead of trying to add to it, because you're going to do something minus something, and that needs to equal -5. So multiplying to 36 could be 1 and 36, 2 and 18, 3 and 12, 4 and 9, or 6 and 6. Those are the only combinations. And if I did a 4 times 9, 4 times 9 is 36, and positive 4 times -9 is actually -36, and 4 minus 9 is -5. So then there's 2 zeros, -4, 2 unique zeros, -4 and +9. These are the 2 numbers, the only 2 numbers, that make the derivative equal 0. That's why they're called critical numbers. Once we get our critical numbers, we're going to make a number line and put them on there with the smaller number first, the bigger number second. And then you need to pick one number in each of these 3 regions. So I would pick -5 as my test point for less than -4. I always pick 0 when I can, and that's between -4 and 9. And then I would pick 10. You can plug them into the first version of the derivative or into the simplified version. It doesn't matter. All we care about is, are these test points? We know that the derivative is 0 here and here. And they're the only 2 numbers where it's 0. So the other 3 test points, they're going to be positives or negatives. They can't be 0 because we already found the only ones that can be 0. And when we plug in -5, 0, and 10 into the derivative function, they're either going to be positive or negative. If they're positive, that's a portion of the graph that's increasing. If they're negative, then we found a section of the graph that's decreasing. And you really can't tell till you check all 3. Whatever answer you get for the first one's not going to help you decide what's happening to the others. So I would just plug them into this version right here. And here's where having a graphing calculator could help. So if I have to do this a lot, then it just speeds the process up, and it's probably more accurate to type. I'm going to type parenthesis. Well, actually, let me do the easiest one first. In fact, I don't even need a calculator for the easiest one. If I plug 0 in, 0 squared is 0. 5 times 0 is 0. In fact, the answer is just negative 36 when you plug 0 in. So f prime of 0 is negative 36, but it's more important that it's negative than it's negative 36. We don't really care about the 36. So everything between negative 4 and 9 is decreasing in the original graph. The original graph is decreasing everywhere between negative 4 and 9 because the derivative is a negative in that section. And you can't switch from negative to positive unless you hit 0 at some point. So that's why these are called critical numbers. Only at negative 4 and 9 is it 0. So once I go past negative 4 into negative 3, negative 2, negative 1, any number that I check there, if it's negative there, it's going to be negative in the entire time between negative 4 and 9, because the only chance it has to change to positive is to go past 9, another spot where it's 0. So now I want to plug 10 in, for example. I want to plug 10 into this. And it may switch to positive, but it can still be negative too. You'll see a lot of the ones we do early on might alternate a lot, but it's not that it's guaranteed to alternate. So if I do 10 squared minus 5 times 10 minus 36, I'm just plugging 10 in. Whoops. I'm just plugging 10 in where these two x's are. 10 squared minus 5 times 10 minus 36. And the answer is positive 14. F prime of 10 is positive 14. So then finally I need to plug negative 5 in, or I can hit second enter and it calls up the last statement I put in here, so I can just back up on top of the 10s and type over them with negative 5s. Although this one will be messed up, so let me put parenthesis, negative, and insert a 5 parenthesis. Okay. That one also tends to be, it often is the case in polynomials that you'll see the same answer twice. And the reason I got 14 again, f prime of negative 5 was also 14. Because I was 1 unit this way away from negative 4 and 1 unit this way away from 9. The balance of it makes that happen sometimes. It doesn't always happen, but often in polynomials it does. But again, the 14s don't matter. It's the fact that this is positive. The left side is positive, the middle portion is negative, and the right side's positive. Positive derivatives tell you that the original function is increasing. Negative derivatives is when the original function is decreasing. When you're done doing all this, cross out your test points because it's real easy to accidentally put them in the answer. Those were arbitrary numbers. I didn't have to pick those. I could have picked other ones. The only answer should have infinities plus negative 4 and 9. So we're going to be increasing. You always start at negative infinity, so we're increasing from negative infinity until we get to the first critical number, negative 4. And that's because the derivative is positive in that whole section. Then it switches to decreasing after that because the derivative switched to negative next. But sometimes the first region is positive and the second one could also be positive. That can happen. It's not a guarantee that it switches every time you go to a new section. It just did so here. So from negative 4 until I get to 9, I'm decreasing. And then I'm going to put a comma because then I'm increasing after 9. From 9 all the way to infinity, it's back to increasing again. And in fact, if you know from college algebra knowledge that when there's a degree of 3 in a polynomial, if the degree is 3 and the leading coefficient is positive, the graph tends to look like this. It's down on the left and up on the right for the end behavior. So that makes sense for what I just said. I'm increasing first till I get to an x of negative 4. Then from negative 4 to 9, I'm decreasing. And then from 9 to infinity, I'm increasing. So even college algebra knowledge can help you make sense of that that's the way it should go. At least on simpler ones. When you get the harder ones, you might not be able to do that, but Whoops, I'm used to my online classes doing this. Okay. In my online classes, I have to share screens with them, but you guys, I'm just doing this right on my phone. So, okay, I don't need to go to the other screen. I can just open it here. Okay, so the critical numbers were -4 and 9. And you just put a comma to separate them. It was increasing from -infinity until -4. And then there was another one from 9 to infinity. And then in between -4 and 9 is when it was decreasing. And even though I drew a graph right at the very end, I did all the answers without the graph first. And in some problems, you won't even know how the graph goes anyway. So this was meant to be done without looking at a graph, actually. I was just showing you that to confirm what's happening. Okay, same exact problem. Now we're up to an x to the 4th problem, though, for number 4. We got a 4th power, 4th degree original function. X to the 4th plus 20x to the 3rd plus 88x squared plus 4. There is no x term, but that's fine. So always do the derivative first. This whole chapter, you're going to be finding the derivative and getting the critical numbers on virtually every problem. So 4x to the 3rd, simple power rule there, plus 60x squared, power rule, plus 88 times 2 is 176. Yeah. 176x. And then there's the derivative of 4 is 0. So this is a polynomial, this derivative. Polynomials are never undefined, so we don't have any undefined critical numbers. And then we can set this equal to 0. There could be up to 3 unique zeros. There could be up to 3 critical numbers where the derivative equals 0. Maybe we can factor out a 4x, hopefully. GCF of 4x. Because if we did that, there would be an x squared left here. 60 divided by 4 is 15x. And let's hope 176 divides by 4. Yes, 44. And then this is going to factor nicely because we're going to have x times x to make x squared. When the last sign is positive, then you get 2 of these for your answer. I'm going to get 2 positives. We need to multiply to 44 and add. There's a plus here, so add to 15. 1 and 44, 2 and 22, 4 and 11. There it is, 4 and 11. 4 times 11 is 44, and 4 plus 11 is 15. I could divide both sides by 4, and 0 divided by anything is 0, so it would make the 4 go away. So there's 3 zeros of this derivative. 0 itself, -4, and -11. There's my 3 critical numbers. 0, -4, and -11. That's part A. The order you put those in doesn't really matter. 0, here it doesn't matter. On your number line it matters, but here you can put them in any order. 0, -4, -11. So on the number line, though, I need to put -11 way off to the left, then -4, and then 0. And I always like to use 0 as a test point, but I can't now because that's one of the numbers that makes the derivative 0. So I would use 1 and maybe -1 and -5 and -12. Just use the smallest possible that you can. You can pick any number you want, but the easier you make it on yourself, the better. Okay, so we're going to plug them into, you can basically plug them into any version of the derivative. You could do this bigger one if you want, or this factored version, or even this with or without the 4. So why not go to the simplest version possible? And again, all we really care about is, are they positive or negative? If I plug 1 in, into any of these versions of the derivative, is the answer positive, negative is all I care about. So you can actually see it here really nice. If I plug 1 here, here, and here, this is 1, and this is 5, and this is 12, but they're all positive numbers. Positive times positive times positive. This section is definitely positive. So that's a spot where the original function is increasing because the derivative is positive anywhere past 0. All positive numbers are going to cause the derivative to be positive when you plug any positive number into the derivative function. But if I plug -1 in, this -1 here would be negative. This would be -1 plus 4, which is positive 3. And -1 plus 11 is positive 10. Positive times positive is positive, but positive times negative, the whole thing's negative. So there's a portion of the graph that's decreasing. Everything between -4 and 0 is decreasing. Now plug in -5. So this part would be -5. -5 plus 4 is -1. -5 plus 11 is positive 6. A positive times a negative is positive. So whenever you pick a number between -4 and -11, that's a portion of the graph, of the original graph, that's increasing, because the derivative in that portion is positive. And probably this last one's going to be negative, but you shouldn't just assume on all problems in this section that that's going to happen. But if you plug a -12 here, that's clearly negative. -12 plus 4 is -8. -12 plus 11 is -1. And yes, a negative times a negative times a negative is negative. So the graph would actually be decreasing first if you traveled left to right. I like to do it this way, and then I can fill the answers in later. It's nice to go left to right instead of trying to answer all the increasing ones first. That can be harder sometimes. So we're decreasing first. You always start at -infinity, whatever you're doing first. From -infinity until you get to your first critical number, -11, that's when it's decreasing. Then it switches between -11 and -4. Now it's increasing. Then from -4 to 0, you're back to decreasing again. You just put a comma here, -4 to 0. And then from 0 forever after, it's increasing. From 0 to infinity, it's increasing. We have 2 sections of increasing, 2 sections of decreasing, and I did them in order left to right, but then in the homework, they're going to want you to answer the increasing in part B only. And you might have to enter that and check it before they'll even let you answer part C sometimes, which I see how they won't let me do part C. So I can't do the decreasing first, even though it happened first. So that's why I like to do it on scratch paper first, and then you can always fill these answers in. -11 to -4 and 0 to infinity. And then from -infinity until -11. And from -4 to 0, that was the 2 sections it was decreasing. In fact, now that I'm done, I did the whole problem without even looking at a graph. But maybe you remember from college algebra that these x to the 4th graphs, they kind of look like W shapes. They kind of form some kind of W shape like that. So yeah, you're decreasing first until you get to this bottom point, which must be -11. Then from -11 until 4, there's a section that's increasing. Then from 4 to 0, it's decreasing again. And then from 0 forever after, it's increasing again. So sometimes college algebra graphing knowledge can make sure that that makes sense if you're doing it on a test and you can't check your answer till the end. Okay, here's a very interesting one. What if the original function is linear? Just our high school algebra knowledge. High school algebra would tell us what this graph is doing. Y equals negative 2x plus 7. This is a graph that has a y-intercept of 7 down to over 1 over and over again. This is a graph that's always decreasing. It's never increasing. It's constantly going down. In any spot you pick, if you put a tangent line there, it's going to have a negative slope. So the derivative should always be negative no matter what, and that's why it'll always be decreasing. So the derivative of this is literally just negative 2. And negative 2 is always negative, literally. There is no critical numbers because I don't have any x to plug in for and solve for 0. And it's clearly never undefined. It's just a constant function. So the derivative is literally always negative. That means the graph is literally always decreasing because negative derivatives mean you're decreasing. This thing's negative for its entire domain from negative infinity to infinity. And even knowing how the graph looks in high school, you would know that. So there are no critical numbers. Not every function has a critical number. They're very special, actually. And the graph is literally never increasing. You don't have to get all the answers. Every section of the answer, doesn't always happen. And it's constantly decreasing for the entire domain, and the domain of all polynomials is negative infinity to infinity. So this graph is always decreasing over its entire domain. So 5 is a very easy one, but I wanted to show you that quick so that it makes sense to you that you don't have to get always, not every function has a critical number, not every function is always increasing, not every function is always decreasing. What about a rational function? The original function is x plus 5 over x plus 1. Again, maybe from college algebra you know what that graph looks like. That could help if you knew that. But let's try to do it without even looking at a graph. If I do the derivative of this, this is a quotient rule. So second times the derivative of the first, which is just 1, that's the slope of it, minus the first times the derivative of the second, which is just 1, over the second squared. And these times ones won't matter since there's other stuff there. So the numerator is x plus 1 minus x minus 5. The x's cancel. 1 minus 5 is negative 4. There's the derivative function. When the derivative is a fraction, fractions are only 0 when the top is 0 and the bottom isn't. And the top of this fraction can never be 0 because it's always negative 4. It doesn't have an x in it to possibly be 0. So that means this function has no derivatives that are equal to 0. And critical numbers are either x values that make the derivative 0. This one never has a derivative that's 0. Or x values that make the derivative undefined. The derivative could be undefined whenever this is 0. If the bottom of the fraction is 0, then the function's undefined. And this x plus 1 would equal 0 if x was negative 1. Because then negative 1 plus 1 would be 0. 0 squared is 0. The bottom would be 0. That would be undefined. So negative 1 could be a critical number because it's a x value that makes the derivative undefined. But it also happens to make the original function undefined. So therefore, it's not a critical number. And in fact, the original function doesn't even exist at negative 1. That's where there's a vertical asymptote, actually. So there's no critical numbers. When there's no critical numbers, that means your original graph is always either always increasing or always decreasing. It's one or the other. And all I need to know is the derivative positive or negative at any x value. You could pick any x value you want except for this one that makes it undefined. So say I pick 0 for x. 0 plus 1 is 1. 1 squared is 1. But negative 4 divided by 1 is negative 4. This fraction, this derivative fraction, will always be negative except at negative 1 where it's undefined. But other than that, it's always negative. So that means the graph is constantly decreasing for its entire domain. It's never increasing because the derivative is always negative. And it's always decreasing from negative infinity to infinity, sort of like that linear one we just did. But it could have been always increasing too if the top of that fraction had been positive. It may have been the way I typed that. Okay, it's always decreasing. Oh no, I know it's wrong. Okay, so we have to account for that negative 1 actually. So from negative infinity to negative 1, and then we pick back up again at negative 1 to infinity. So you can't include negative 1 in there because nothing's happening at negative 1. And this is a way to say everything but negative 1. You just exclude negative 1 here, and then you exclude it that way too, and that way it's everything but negative 1. Maybe you know from college algebra what this graph looks like. This has a vertical asymptote of x equals negative 1, because that's where the original denominator is undefined. Nothing's happening at negative 1. You never cross or touch a vertical asymptote. And then remember the horizontal asymptote, the 3 cases. If the degree of the top is the same as the degree of the bottom, then you get y equals the 2 leading coefficients divided by each other. If the bottom has a bigger degree, it's y equals 0. If the top is bigger, there is none. But if they're equal in degree, then you get y equals the ratio of the 2 leading coefficients, which would be 1 here literally. So we've got a horizontal asymptote of y equals 1, a vertical asymptote of x equals negative 1. And if you plug 0 into the original function, the y-intercept would be 5 divided by 1, which is 5. So there's a y-intercept of 5. And whenever you just have one vertical and one horizontal asymptote, you often get one curve like so. And then on the other side, it's usually on the other half of the horizontal asymptote. And you could test a point like negative 2 or negative 3, plug negative 2 or negative 3 into the original one, you'll see that it's down here. So again, you don't need to solve this problem by looking at a graph, but if you look at a graph, it makes sense. Because look how if I travel left to right, I'm going down, 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 and then nothing's happening at negative 1. And then you pick up again after negative 1, you're going down, 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 down. It's constantly going down no matter where you are except negative 1. So that's why it's decreasing from negative infinity to negative 1, and then again from negative 1 to infinity. So if you do have knowledge of what the graph looks like, it can help confirm these answers sometimes. But actually the point of doing these is doing them without looking at a graph, because maybe you don't know what the graph looks like, especially as we get to harder problems later in the chapter. Here you're doing more simpler ones because you're learning the rules at first. So number 7, we got f of x equals negative 4 plus 6x to the 2/5. Now maybe you don't know what that graph looks like. So let's find its derivative then and see if there's any critical numbers. The last 2 problems haven't had any critical numbers. The derivative of negative 4 is nothing. The derivative of the other term would be 6 times 2/5 x to the 2/5 minus 1. Power rule. And this unfortunately doesn't simplify, but it would just be 12 over 5. 2/5 minus 5/5. Change this one to 5/5. 2/5 minus 5/5 is negative 3/5. So then we're probably not going to want to work with negative exponents here, so I would keep the 12 in the top, keep the 5 in the bottom, and then put that x to the 3/5 in the bottom. By moving it down to the bottom, then you wouldn't have a negative exponent anymore. So here's the derivative function. The original function has an infinite domain. There's no issues with this domain. This domain would be everything, because you only get issues in your domain if a denominator is 0, and this thing doesn't even have a denominator, or if you have even roots that could be negative. We have an odd root here actually with a 5th root, or if there was some kind of log in it. If you don't have a square root, even root, a log, or a denominator, then your domain is basically infinite. So there's nothing that makes the original function undefined. So if I get any undefined spots in the derivative function, that will be a critical number this time, unlike the other one where the one number that made the denominator 0 in the derivative also made the original problem undefined. But the top of this fraction is just 12, so that means it can never be equal to 0. You can only equal 0 if your fraction has an x in the top. If the top of the fraction is a constant, that literally means it can never be 0. So there are no critical numbers from getting the derivative to be 0, but there is one critical number from when the denominator is 0. Literally 0 itself would make the denominator 0, because 0 to the 3rd power is 0, the 5th root of 0 is 0, and 0 times 5 is 0. So 0 makes the denominator 0, which makes the derivative undefined, and it does not make the original function undefined. If you plug 0 in here, you're going to get 0 plus -4, which is -4. So there's the first time we've seen a critical number that came from a spot that's undefined in the derivative, but it's not undefined in the original problem. So we've got one and only one critical number, 0 itself. So that means there's a chance it could be increasing in half of the problem and decreasing in the other half, or maybe they're both increasing, or maybe they're both decreasing. Don't just assume there's going to be one of each. So make a number line with just 0 on it. I would pick 1 and -1. Plug them into the derivative function. 1s are really nice to work with too, because any root of 1 is 1. 1 to any power is 1. So 1 to the 3/5 power, doesn't matter the 3/5 power, that's 1. Times 5 is 5, and 12 divided by 5, we don't care that it's 2.4. The more important thing is that it's positive. So our original graph, this one we might not even know what it looks like, it's always increasing anytime you're past 0. And then if I plug -1 in, as long as it's an odd root, which it is, you can do an odd root of a negative, and that just makes the whole answer -1 actually. So -1 to the 3/5 power is -1. Times 5 is -5, but 12 divided by -5 is definitely negative. So that means our original graph is going to be decreasing first. It's going to be coming down somehow. At 0, it'll be flat for that one moment in time, and then after that, it'll increase somehow. It's not necessarily like this. I'm just tracing just without any kind of graphing knowledge of the original problem. So we're decreasing until we get to 0, and then we're increasing forever after. So we're increasing from 0 to infinity without including 0. Since they always make you answer the increasing one first. And then you're decreasing from -infinity to 0. Okay, number 8. We saw one earlier that used the quotient rule. Here comes one that's going to use the product rule. Original function has x minus 6. That's a function of x. X minus 6 times exponential e to the -5x. Two functions of x multiplied together. So I have to employ the product rule. First times the derivative of the second, and the derivative of an exponential is first itself, times ln of e, which is 1, times the derivative of the exponent, which is -5. So if I rewrite this, it would be x minus 6 times -5 e to the -5x. First times derivative of the second plus second times the derivative of the first, which is easy. That's just 1. And then it won't matter since there's other stuff there. So here's the derivative function right here. And it has a GCF of e to the -5x. So I could pull that out front, e to the -5x. I could distribute this and get -5x plus 30. And then when you pulled this e to the 5x out, it would be plus 1. So e to the -5x times -5x plus 31. Okay, so I've got a product equal to 0. I can try to set each part equal to 0 and find what makes the derivative equal 0. Well, exponential functions, unless you shift them, they never equal 0. Exponential functions either go like this, or like this, or negative. They could be reflected, if there was a negative out front anyway, they could be reflected over the x-axis. But this negative actually makes it go like this. But without a shift up or down, then it has a y equals 0 horizontal asymptote. An exponential function never equals 0, and it's never undefined either. It has an infinite domain left to right. So no critical numbers are going to come from this part here. This is just never equal to 0. This is linear, so this will equal 0 once. At positive 31 over 5. So positive 31 over 5 is my one and only number that makes this derivative equal 0 or makes the derivative undefined, because nothing makes the derivative undefined. So that would be my only critical number. So now I can make a number line with just that. 31 over 5. 30 divided by 5 is 6, so this is 6.2. This is exactly 6.2. So I would pick 0 for less than that. You could pick 6, but I would just use 0. It's easier. And then I would use 7 for something bigger than 6.2. If I plug 0 into the derivative function, either into any version of it, I guess this is the easiest version right here. Plug 0 in. The exponent here is going to be 0. -5 times 0 is 0. E to the 0 is 1. And then if you plug 0 here, this part will go to 0, and that'll just be 31. 1 times 31 is 31. So the derivative is positive when you plug 0 in. So that means you're increasing, and you probably definitely don't know what this original graph looks like, but apparently it's increasing. This part is decreasing. Don't get fooled by that. E to the -5x does this, but when you multiply it by this, the graph just can get totally different to a point you probably don't even know what it looks like. So the derivative is telling me it's increasing from -infinity until I get to my critical number. And now if I plug 7 in, this will get messy, but 7 times -5 is -35, plus 31 is -4. Really all I care about is that that's negative. If I plug 7 in here, even though the exponent's negative, e to the negative 35 is not negative. Negative exponents have nothing to do with negative numbers. E raised to the negative 35th power, it just makes it 1 over if it's negative. So this is a positive answer. So that's positive. Positive times negative is negative. So this portion is negative. Cross out the test point. And if you're negative on the right of that critical number, then the graph has to be decreasing. So this is some kind of graph that's increasing at first in some way. We don't even know what it looks like. And then after we hit that one critical number, then it decreases after that. So we've got 1 increasing and then followed by 1 decreasing. Whenever there's one critical number, you're either going to be always increasing or you're going to be always decreasing, or there's going to be one of each. So we're increasing first. So that means from negative infinity until you hit the critical number. And see how it says use integers or fractions? You always got to read that part. Even though it's exactly 6.2, they won't take that answer because they prefer fractions actually. Never put a decimal unless they ask for it. So 31 over 5, that's the only portion of the graph that it's increasing. And then from 31 over 5 all the way to positive infinity, it's going to be decreasing forever after without even knowing what the graph looks like. So those first 8 problems, they were basically all the same. They just gave us different examples of what could happen. So now we're going to have 2 of these business problems, but it's going to use this concept of increasing and decreasing. So a manufacturer sells video games with the following cost and revenue functions in dollars. X is the number of games sold. We have the cost function, we have the revenue function. Determine the interval on which profit function is increasing. We want to increase our profits if we're a business. So that's something a business would be very interested in knowing. When is the profit increasing? It's going to be increasing anytime the derivative is positive. So that's what we need to find. And we need to find the profit function first. So number 9, the cost function is 0.11x squared minus, and they got a funky decimal here, there's 4 zeros, 0, 0, 0, 0, 6, x to the third. The revenue function, revenue is the money you bring into your business, 0.824x squared minus, and this one has 3 zeros, 2x to the third, so 0, 0, 0, 2x to the third. So first, profits. Profits for a business are how much money do you bring in minus how much money do you spend. And you hope that you bring in more than you spend if you want to make a profit. So if I subtract these two, then I'll have my profit function. And then if I take the derivative of the profit function, then I can figure out its critical numbers and when is it increasing and decreasing. And we just really care when is it increasing, but we'll be going through all the regions to find the increasing ones. So take the 0.824 from the revenue function and minus the 0.11. So there would be a 0.714x squared. And then minus, now do this one minus that one. Or maybe it's not minus, but let's do 0.0002 negative. So negative that minus a negative, so I'll just change it to plus, I guess it'd be the easiest thing, plus 0.00006. So that is negative 3 zeros and a 14. There's my profit function. The derivative of that, p prime of x, is just power rule, even though it's kind of messy with these decimals. 2 times 0.714, 1.428, x to the first power, decrease the exponent by 1, minus, and then we need to do 3 times 0.00014, which is 0.00042. And that'll be x squared, decrease the exponent by 1. This is a polynomial, so it's never undefined. So we won't get any critical numbers from undefined places. But because it's squared, there can be 2 critical numbers from when it's equal to 0. And we can factor out an x and possibly some numbers, but I guess we don't need to do the numbers. So let's just take out an x. So there might be a larger GCF than that, but that's fine. Just take out x, because then one of the critical numbers is 0 itself. 0 makes that equal 0. And then whatever makes this 0, that's just linear. So all you have to do is subtract 1.4 from both sides. And you'll get negative 0.00042x equals negative 1.428. Divide both sides by negative 0.00042. Oops. And do that here too. 0.00042. And the 2 negatives are going to be a positive. So I can just type in 1.428 divided by 0.00042. And does this come out nicely? Yeah, it's large, but it came out nicely to 3,400. So my number line would be 0 and 3,400. I can't plug 0 in because it's one of my critical numbers. But I could plug in negative 1, positive 1, and then we'd have to do like 3,401. And plug it into any version of the derivative. I'm just going to do this one, I guess, since it's easier to type probably. And here's where a graphing calculator could help. So if we plug 1 in, that's nice, because if you plug 1 in, then you just get the decimals. Anything times 1 is itself. So plugging 1 in, it's just going to be, I don't even need the graphing calculator, it's going to be 1.428 minus this 0.00042. So, and again, you don't care what the answer equals, it's just all about positives or negatives. When I'm plugging 1 into the derivative function, the derivative is positive. So everywhere I'm between 0 and 3,400, my original graph is going to be increasing, which means profits are increasing. If I plug in negative 1, then all that's going to happen is these 2 decimals are going to switch signs. This one will be negative, and this one will be positive. So then you're going to get 0.00042 minus 1.428, and that's negative. If you could even make negative games, which isn't even possible, but so profits would decrease if we could make negative numbers of games. That would be bad, because you're spending money on your cost of your business, but you're not making anything. That'd be like hiring people, and while they're making the games, they break them, and then we have no game. But we still have to pay them their salaries, even though they're incompetent. Okay, finally plug in 3,401. So 1.428 times 3,401 minus 0.00042 times 3401 squared. And I got a negative 1.4 again. So if you make more than 3,400 games, the problem is it's going to just cost a lot. So there is a point. You don't just, if you're a business, you don't just make an infinite amount of your product, because then where are you going to store it? And it can cost more costs with employee salaries to do that. So this is what businesses want to know, is they want to maximize their profits. We're going to do that later too. But if you make anywhere between 0 and 3,400 games per day, per week, per month, whatever I don't know if there's a time interval to this problem, but that's when your profits are going to be positive and increasing. And there's even a point where we try to find what's the maximum amount. What's the ideal number of games for our business to make in a day or a week or a month, so we really maximize our profits. Right now, we're just worried about when they're positive. So the profit function is increasing anywhere between 0 and 3,400, which were the two critical numbers. And it would be decreasing anytime the games were negative or anytime we made more than 3,400 games. Then our costs would just exceed our revenue. Making more than 3,400 games, you're still bringing revenue in for that, but the costs start increasing more than the revenue is, so then you're losing money by doing that. Here they want to know, when is it increasing? When is it decreasing? Okay, we got assets from a trust fund in trillions of dollars. And T is the number of years since the year 2000. And they put a limit on our domain from 0 to 50, which the other problems haven't had yet. So one nice thing is if you have a limited domain like this from 0 to 50, then if you get any critical numbers outside of that interval, then you can ignore them. So if I get any negative critical numbers or any bigger than 50, then it's like they're not even critical numbers anymore. So I've got a cubic function. Let's take the derivative of it, and then it'll get it down to a quadratic function. And that means it's going to have two critical numbers potentially. So my account for this trust fund that has trillions of dollars in it, which would be like managed by somebody, is 0.0000395 t cubed. 4 zeros, 395 t cubed. Let's just do this part by part maybe. So the derivative is going to be 3 times this decimal. 3 times 0.0000395. So 3 zeros and a 1185. That's going to be the squared term. Then the squared term here is negative 0.045. Now they put another 0 after the 5, but zeros at the end of decimals don't matter, so I could ignore that. So now do 2 times 0.045. That gives you 0.009 negative for the t. And then the linear part, the derivative of that's easy, is just the decimal. And then the derivative of this is nothing. So I just have to add a 0.682 to the end of mine. It's a messy decimal polynomial, but it is a polynomial. Polynomials are never undefined, so I don't have any critical numbers coming from undefined locations. I do have a square, so there can be 2 times this equals 0. And unfortunately, there's no easy way to solve for those two. You really just have to use the quadratic formula. This is A, this is B, and this is C. And I think they say to round to the 10th while you're doing that. Doesn't really, oh, here it is, round to the nearest 10th. Okay. Thought I saw that somewhere. Okay, so remember the quadratic formula? T equals the opposite of B. We have to do this a lot in calculus. Opposite of B plus and minus square root B squared minus 4AC all over 2A. So the opposite of negative 009 is positive 009. Then we need 009 squared minus 4 times this a, I'm just going to point at it because it's big and messy, and times this c, all over 2 times a. Okay, so I'm going to do the inside of the radical first. 009 squared minus 4 times 0001185 times 0682. And then I can square root that. Okay, so now I have 009 plus and minus 0069766,181. And the denominator is 2 times 0001185, which it's putting in scientific notation, but that's 000237. So I'm going to do one of these with plus and one with minus. If I do 009 plus 0069766,181, close parenthesis, and then divide by 000237. At this point, they want you to round to the 10th. So the plus 1 is 67.41, or we'll round to 67.4. So there's one of the two critical numbers, approximately 67.4. Here's where decimals are okay because the original problem's in very messy decimals. And then if I redo this with a minus, then I'm getting 8.53. So we'll say 8.5. So there's my two critical numbers, 8.5 and 67.4. So one thing that helps is, remember, there was a limited domain between 0 and 50. 67's past that, so it doesn't matter. So I only have one critical number that matters, and we can plug in 0 or 1 below that, and then I'd plug in 9 above that into the derivative function, and probably just right here would be best. Plugging in 0 is very easy because the squared and the linear term disappear. The answer is literally 0682 if you plug 0 in. That's positive. So the function is increasing between 0 and 8.5. That's definitely an increasing portion. So it's increasing from 0 to 8.5. And it could be increasing from 8.5 to 50 also. We don't know that yet. But from 8.5 to 50, it's either increasing or decreasing. So I'm not going to hit the answer button yet because I didn't check this answer yet. So what if I plug 9 into here? It's probably going to be negative, but we don't know that for sure, especially in future parts of this chapter. But I'm guessing it's going to be negative. So 0001185 times 9 squared minus 009 times 9 plus 0682. So I just plugged a 9 in right here and right there. And just checking is the answer positive or negative? It's negative. Negative 003. It's a messy decimal, doesn't matter. It is negative. So then the graph is decreasing from 8.5. It would actually decrease all the way to 67, but we only care about 0 through 50. We're just going from the year 2000 to the year 2050. So yes, it's only increasing till 8.5. After halfway through the year 2008, it stops increasing. And then it's going to decrease from halfway through 2008 all the way to the year 2050. So the trust fund starts losing its money is it's earning interest at first, but then it starts paying out more than it's bringing in. So you want to get in on the action while it's increasing apparently, and maybe cash in before 2009 happens is what would be a application of this. So there's all 10 problems. Got 100% on this now, and it took a little over an hour to do all 10 of those. So now section 5.1 is finished. We finished the first unit, the second unit, and now I just started the third unit, 5.1, and I've got 100 on that. We're going to be doing 5.2 later this week. Next week will be 5.3 and 5.4. The week after is 6.1 and 6.4. And then the fourth week out is 6.5 and review. And then there'll be a test that'll open up on November 10th. The test has already been created, but it won't appear till November 10th when you're able to open it and take it. November 10th and 11th, you'll have a 2-day window to do that, and that's 2 weeks before Thanksgiving too. And then we're going to be doing only 6 sections at the end, and I've got 3 of them set up already. And then there's also 7.3, 7.4, and 7.5. Those are the last 3 sections we do. So that'll be happening. We'll be doing a little bit before Thanksgiving and the rest after Thanksgiving. So there's only 3 more assignments that you can't see yet, and then there'll be one last review and test, and then there'll be a review and a final also. So I'm still quite ahead of what you need at this point, and I'll be adding these other ones in soon. So that's it for section 5.1, and we're going to be doing a lot of similar stuff in section 5.2. 5.2 is doing this all over again, but then in 5.2 we're actually looking for, does the number line, does it switch from increasing to decreasing? It's not a good example there, but does it switch from decreasing to increasing or vice versa, which here it was doing it all the time, but it doesn't always do it every time. So if it switches from decreasing to increasing or vice versa, then that's a special thing we're going to do in section 5.2. So that's it for section 5.1.